Let me start then. Yes, and first, thank you very much for this introduction to this to talk in this symposium. I'm quite excited to talk about this new book of mine. I'm always actually excited to talk about it. So yes, so the title of the book is Painful Intelligence: What AI Can Tell Us About Human Suffering. It is at the moment only an ebook, so it's available on arXiv as well as on my homepage. A paper version is probably forthcoming, but not yet available. Okay, so, sorry. Here's a short abstract. So what this book is all about and what this talk is about is models on information processing underlying suffering. So the main idea here is that suffering, in particular human suffering, is mainly based on frustration. So then the question is, how do we define frustration? And I will present two different definitions. One is not achieving a goal, and the other one is not getting reward that was expected. There's also an alternative definition of suffering, which is very strongly related, which is that suffering is based on threats. Now, the point is that using AI theory, or computational neuroscience, if you like, we can actually understand the causes of frustration. And if we understand the causes, then we can develop interventions to reduce suffering. That is actually then the end of the last part of the book and of this talk. In some sense, like the most important, we will see various interventions, which then end up being very similar to what has been proposed in Buddhist and Stoic philosophy. So the first part of the talk and the book is about defining suffering. Well, we can go basically back as early as possible, according to respect scientific priorities, so to say. And well, one of the earliest persons who made influential work on this was the Buddha in India. Here's a short quote, a very well-known quote from him, in which he says that union with what is displeasing is suffering, separation from what is pleasing is suffering, and not to get what one wants is suffering. And there were Stoic philosophers in Rome and Greece had very similar ideas, one of the most famous one being Epictetus. Here's a quote from him he says, "He who fails of the object of his desires is disappointed, and he who incurs the object of his aversion is wretched." So what I do here is interpret all of these actually as forms of frustration. We can perhaps talk about like a positive and negative form of frustration. Positive is what is in blue here, where basically you want something and you don't get it. And the kind of negative version is that where you don't want to get something, so you want to avoid something, but then still you somehow incur it, so to say. And well, based on these ancient philosophies, then we would posit that this is the main mechanism producing suffering. So I should point out that when I talk about suffering, it means something like what might also be called mental pain. It doesn't include physical pain. That's a completely different topic, not considered here. Okay, so how do we approach these ideas then, these concepts from the viewpoint of AI? Well, one of the most fundamental ideas in AI is planning. It is the very most basic model of an agent selecting actions going back to the 60s or 70s. So the idea is that the world is conceptualized as a set of states, typically discrete states. The agent has a number of actions that it can take, and each action takes the agent to a new state. Now, one of the states is designated as the goal state, and then the computational problem of planning is to find a sequence of actions, that is a plan, that takes the agent from the current state to the goal state. It's like, I hope you are familiar with the idea of a Rubik's Cube. So you have this cube where you can make now actions with your hands and change the state of the cube. So any constellation of the colors on the cube can be seen as a state. In this framework, you can take actions to change the state. And then there is a goal state, which is this kind of a state where the whole point in the Rubik's Cube is that you want to transform the cube into this state. And well, then the problem problem of planning is to find a sequence of actions that will take you from a random initial state to this goal state. Now, planning is known to be computationally very demanding, as we can see in this Rubik's Cube case. And well, I will talk about that a bit more later. So now, using simply this definition of planning, we can actually go on and define what is frustration and the closely related idea of desire. So, definition of frustration is as follows. We have an agent that chooses a goal state by a method to be defined. Then it makes a plan to reach that goal, and then it acts according to that plan. But then it happens that the agent fails to reach the goal, and this is frustration. At the same time, we can then define the idea of desire, which I use synonymously here with wanting, which is that it is exactly the system that chooses the goal state among many available options. For example, if your perceptual system detects that there is chocolate nearby, well, then you may designate that the state, you may have the feeling that I want it, which then computationally is seen as the idea that you try to plan for the state or for one of the states where you actually have that chocolate. Now, these two definitions then actually lead to the idea that frustration is exactly not getting what one wants. And this is nothing else than the dictionary definition of frustration. It is also in line with the definitions by the Buddha and Epictetus that we had earlier. Right, so we have it appears a conceptually satisfactory definition of frustration here. But that's of course only in the very, very basic case of planning. Well, AI of course has much more stuff to it, and especially in the case when we talk about action selection, there is the field of reinforcement learning, which is kind of an alternative to planning. It basically attempts to, the idea is to learn intelligent action without planning. Also, the framework is changed a little bit so that there are no explicit goal states, but what happens is that some of the states give you reward, and then you try to maximize the future reward based on your actions, your policy. And then the idea, well, to put the theory very, very simply, is that you learn what is the best action in each state by a certain version of dynamic programming. Most RL algorithms are based on dynamic programming. Now, the pros of this kind of an approach is that, well, there is no exponential explosion in the planning tree simply because there is no planning tree at all. And that's why then you can actually take actions very fast. Well, the cons are, well, you have to pay something for that, which is basically that the learning is actually very slow. You must repeatedly visit every state. And also then the ensuing learning can be quite inflexible. So like here's a simple example where basically if the agent goes to this green state, it gets a high positive reward of 10. If it goes to the negative, to the red states, it gets a negative reward of -1. And so the idea is that the agent moves in this kind of a grid world, taking steps up, down, left or right. And now the basic idea of reinforcement learning is that you learn for each state quantities called values, which basically tell you, well, they can tell different things, but in the basic case, they tell you how good this value is from the viewpoint of future reward. A high value means that, well, that's a good state, you want to get there, then you get a lot of reward. As we can see here, like states close to this positive reward of 10, they have actually high values. While states which are far away or close to these negative rewards, they have lower values. So then the idea is that the agent can basically choose its actions simply by looking at which of the possible future states has the highest value, and no planning is necessary. It's not necessary to look further ahead many steps like in planning. Okay, so now then the question is, how can we define frustration in this more general framework of reinforcement learning? Well, that is possible by a well-known quantity called the reward prediction error. Also, if you know the theory of reinforcement learning, it's also often called the TD error in that context. In the simplest definition, it can be simply considered as the difference of the obtained reward and the expected reward. So it is really, in this formulation, it is really that you have an expectation that is a prediction of the reward, and then you look at what was the error in that prediction. And now, using this quantity, then we can define that the negative reward prediction error is frustration. So that means that if there is what is also called reward loss, that is, the reward was less than expected, then that is frustration. This formula, this concept has been used in neuroscience in various contexts. For example, in some very recent work, Rutledge and others use this as a measure of well-being. So basically kind of the opposite of suffering. Now, this is an extremely important concept. The reward prediction error is extremely important quantity in reinforcement learning. In fact, it can be shown that reinforcement learning all these value functions, is possible by simply minimization of the squared reward prediction error when you sum it over all the states and actions. Now, of course, here when we talk about frustration, we are only talking about like one kind of reward prediction error, that is the negative part. But this shows then basically the evolutionary function of this reward prediction error and also the evolutionary function of frustration. It is basically a signal for learning. So when you see, well, intuitively, when you are frustrated, you kind of fail in what you are doing, well, you can use that information for learning to act better in the future. But now in this reinforcement learning framework, such learning is always incremental, like stochastic gradient descent, meaning that for each action, which now produces like one data point, you make a small adjustment to the parameters of your system. We will see later why that is important. Okay, but then we have also, that was the case of frustration, but we also have a second model of suffering, which is about threat. The idea of threat is emphasized in contemporary approaches, like in a famous framework put forward by Cassel in, a few decades ago. So how do we define the idea of threat in a conventional AI framework? Well, it happens, we can do it as follows. We consider xt, which is the total future reward starting from that time point t and the state where you are in. Now, the important point here is that we consider this as a random variable. We don't look at its expectation only, we look at its whole distribution, which is the domain of a theory called distributional reinforcement learning. And now we look at, in particular to model threats, we look at the negative tails of this quantity, the total future reward, and how heavy they are. So that is how much probability mass is there for very negative values of this quantity. Negative values. Sorry, actually, I shouldn't talk about negative values of the quantity x, but what we do is that we subtract from this value, x, its expectation. And then we can look at the negative values, the cases where the realization of the total future reward is much less than what is expected. And that is actually then taken as our definition of threat, or measure of threat. So in other words, a threat is basically a sufficient probability of large future reward loss. So it's reward loss, comparing the reward to its expectation, and all this in the future based on predictions, and then talking about a sufficient probability that there's a sufficient probability that it will be sufficiently large. Okay, it's a bit of a complicated sentence, I have to say. But this is actually very similar to measures that are used in what is called risk-aware reinforcement learning. So people have looked at a case where there is an agent, and well, classical reinforcement learning is simply maximizing the expected reward. But if you want to be risk aware, you also want to look at some other quantities, not only expectation. The classical thing to look at is to look at the variance of the reward. But that is actually not a very suitable thing here when we talk about threat, because threat is really about like having highly bad things, very bad things happening. So that is, we should look at only at the negative tails of the distribution of this reward loss. It's something like that is sometimes done in risk-aware reinforcement learning. It's just a bit more difficult, so people often just use variance. But in any case, so there's an interesting connection to frustration here, because we are comparing the reward, now the total future reward, to its expectation, which is now considered the baseline. It's very similar to frustration, not exactly equivalent because, well, this is about the whole future reward, but anyway, it's very closely related. So that's why then I will focus on frustration in the rest of this talk. The claim is that if we talk about things like interventions to reduce frustration, then we would be reducing also threat at the same time. In the book, I will have more details, and so it's not exactly the same thing. But for the purposes of this talk, I will make this simplification. Okay, so that was the first part, defining suffering in terms of frustration and threat. So now the second part of the talk is about problems in information processing, which can be seen as basis for suffering, as causes for suffering. I have actually a lot of chapters in the book on this topic. Here I will basically go through a kind of a random sample of a couple of problems of information processing. So the first one, which I already alluded to, is the fact that planning is very difficult, and that's why it can easily fail. So a well-known idea in any textbook on AI actually is that, well, the number of possible action sequences grows exponentially as the function of time steps. So it can be illustrated like this. So you kind of start here at the root, which is the current state, and then you build this kind of a tree of all possible action sequences. And if you have just like two actions, left and right, well, of course, you have a binary tree where the number of possible sequences and the number of leaves in this tree grows exponentially. So that's why when you have basically, if you look a bit further into the future, like let's say 10 time steps, well, then what happens is that, well, the number of possible action sequences just goes larger and larger, especially, well, with 20 time steps, it's even in the binary case, it's 1 million sequences. So it may simply get too difficult to compute. That's also why it is so hard. Well, one of the reasons why it's so hard to solve the Rubik's Cube, because, well, you can't just like in your mind plan properly many steps ahead. You can perhaps plan 1 or 2 steps ahead, but probably not more than that. You would need to plan, I don't know, 20, 30 steps ahead. Yes, so planning can simply fail because it's computationally so demanding and you are not able to find a proper plan. But there's another reason, which is that, well, the world is not simply like this kind of a deterministic tree. The world is actually stochastic. For example, obstacles may appear, and that then means that even if you found the optimal plan, well, it may simply fail because of stochastic disturbances in the environment. So these are some of the reasons why your plan might fail and you might have frustration. Another reason is that, well, if you want to have a system working in the real world, well, you need some kind of a perception, like computer vision or something. You need to be able to process sensory data and from that extract information about, for example, what is the state in terms of reinforcement learning. But the incoming sensory data is typically insufficient. It's widely considered that, even in human vision for humans, well, the incoming sensory data is insufficient and you need something else, which is typically formalized as some kind of a probabilistic inference. typically Bayesian inference, where you have some prior information about the world. But whatever methods you may use for that probabilistic inference, well, it is by definition uncertain because it is probabilistic, and it can even be illusory. In the case of human vision research, there's a lot of demonstrations on how people tend to see things in images which are not really there. Like here's a classical Kanitsa's triangle illustration. Now it may or may not work depending on like your distance from the screen, what the stimulus actually looks like on your retina. But basically, when you look at this, you might actually see that there's a contour going here and here and here, so that you actually see a full triangle. But actually, like if you, in this area here, there is actually no edge. It's only white pixels, but your visual system is creating, at least under ideal circumstances, the visual system is creating actually some kind of an edge here. You see a contour here. So that's a classical visual illusion. Now, what this uncertainty means from the viewpoint of suffering is that, well, uncertainty means unpredictability. Unpredictability is perhaps just like one form of uncertainty. And then by definition, unpredictability, it increases the reward prediction error. And of course, it also increases the failure of plans because, well, yes, as I said, the world is stochastic and you cannot predict, if you cannot predict the consequences of your actions, then of course your plan is more likely to fail. It is even true that the reward itself and any computation of reward loss, those are only percepts, which are computed, estimated based on incoming data. So your reward and reward loss may actually be also misestimated. They might even be illusory. I will come back to that point a bit later. Okay, and a third point in this random sample of various reasons for suffering is uncontrollability. And I'm here talking about showing an example of the uncontrollability called wandering thoughts. What wandering thoughts mean is that often unintended thoughts invade your mind, even when in the middle of performing a task. So like in this funny illustration, so people are trying to focus on their work, perhaps reading something on the screen, but then they just get ideas, start fantasizing about different kinds of stuff like Superman here or vacation here. But okay, maybe some people are then actually able to focus on what they are supposed to be focusing on. Now, in psychological research on wandering thoughts, people have found that typically these wandering thoughts can be divided into two categories. Not all of them, but most of them, which is that they might be about planning the future in more or less realistic ways, could be like rather fantasy kind of ways, or they could be about remembering the past events. So yes, this is an interesting reflection of the uncontrollability, even of the uncontrollability of your own mind. So you are not able to control even your own mind. If you can't control even your own mind, how could you possibly control like the outside world? So now why does this actually happen? A simple way of thinking about and kind of intuitive common sense way of thinking about this might be that, okay, your mind just gets tired, you don't have the energy to concentrate. But that may not be the whole story. Here's a computational hypothesis, I think a rather widespread idea, which is that wandering thoughts actually serve a useful computational function, which is that when there is nothing urgent to do at this point, when you are kind of you're supposed to do something, but it's a bit boring and you don't have like any sense of urgency in any kind of evolutionary sense, then your brain might start doing simulations. It might start planning future events or replay past events. These two categories that we saw on the previous slide as being typical wandering thoughts. Now, it's probably rather obvious and kind of makes a lot of sense why you might do planning in this kind of a case. because planning is computationally expensive. So when you are doing something which doesn't seem to be very important, you might start planning about future events, future actions, and make plans about like what you are going to do tomorrow, for example. Now, it may be quite counterintuitive why you would do replay of past events. So basically replay like what happened yesterday in your mind. But now here we see a very simple explanation from the theory of AI, which is that, well, learning is incremental in reinforcement learning, as in most of AI, modern machine learning. So it happens kind of data point by data point. You calculate something little bit like a stochastic gradient, even in reinforcement learning, and make small adjustments to your parameters. So what it means is that once you have, when you have an event that happened yesterday, you may actually want to replay it many times in your system, in the learning system. In particular, actually, the system called the hippocampus, which stores some of the memories like this. Because only then you can actually learn by inputting it to the learning system many times. In fact, this kind of a replay is well documented in the brain. It has been widely observed in rodents, as we can see in this picture. And it's also widely used in AI, where it's often called like experience replay. But now, from the viewpoint of suffering, what it means is that the wandering thoughts are basically multiplying suffering. Because in these past events that you replay and in the future events that you're planning, in your simulations of planning, well, you are often repeating past frustration and imagining new kind of frustration. If you plan something tomorrow, well, you will often have like to try out many plans, many of which fail. So it's useful. That's why I'm saying in the title that wandering thoughts are useful computationally, but they can actually be painful as well. Okay, so as I said in the book, I actually go through many more reasons for, many more phenomena that are somehow like the causes of suffering or that amplify suffering, like these wandering thoughts. So here's a graph that I took from the book. Now I'm basically kind of a bit fading out those parts which I didn't consider here. What I talked about here is like the idea that, well, I didn't actually perhaps mention this explicitly, but the ideas here were that, well, you have insufficient computation in planning and insufficient data, incoming data for perception, and the world is complex. So that's why you get like uncertainty of perception, unpredictability at the same, which is one aspect. And then you have the world is uncontrollable as well. And then these things create error signals like reward prediction error and frustration, failure of plans. And then I talked about the idea of wandering thoughts as a simulation that then kind of amplify the error signals and frustration. So in the book, I have other stuff like what is called like things like insatiability and what I call evolutionary obsessions and so on, and emotional interrupts, and the concept of self, which is certainly extremely important, but I will not go into details here. But okay, anyway, so I write some kind of a very informal equation to summarize all these ideas, what I call the frustration equation. So if we actually then put all together all these theories that we had, then we come to see that frustration is actually a much more complicated phenomenon. It's kind of, it has a basic definition and then it can be amplified in various ways. So the basic definition of frustration was that it's the difference between expected and obtained reward. But now we saw that, well, it's important that that frustration actually is a function of the perception of this difference or of reward loss. And that can be amplified by different things like the number of times it is simulated, as in wandering thoughts. And also, well, we have to take into account the level of certainty attributed to that perception. I will have a bit on that later. And also I'm writing this in gray because I didn't actually talk about it, but we also have to talk about or take into account the amount of attention that is paid to it. There's some material on that in the book, but not here. But so we have a kind of a formula, a simple formula for frustration, where we have the original idea of reward loss, and then a couple of other terms, and they are all multiplying each other. So now the question is that how can we reduce frustration? Well, it's kind of obvious that, well, we reduce any of the terms on the right-hand side of this equation because they are all multiplying each other and they are actually all non-negative, positive. So this is really the basis and the design of interventions. I have a lot of interventions in the book, and again here I will now show just a kind of a random sample of some of the interventions. Right, so we had a definition of suffering, then the causes, and now then based on that, we can actually then go to design interventions. Perhaps the most fundamental intervention is to reduce expectation of rewards. So we had this formula, just recalling it, that reward prediction error is obtained reward minus expected reward. And if this is negative, then there is frustration. Well, it is kind of obvious that without even doing sophisticated mathematics, is that if you just expect less, then that will decrease frustration. It will then, well, increase the reward prediction error, and, well, the negative reward prediction was the frustration. So that's a very easy thing to say, that, well, we just reduce expectations of reward and then frustration is decreased. But how do we actually reduce the expectation? That is the question. And of course, it is a very complex thing. And here we get into questions of various ideas, which are actually kind of similar to what has been previously proposed in Buddhist and Stoic training, but for which we can now formulate from a kind of a scientific viewpoint, a computational viewpoint. Well, two of the basic ideas I'm referring to here are that you should recognize the uncontrollability of the world and even of your own thoughts. The basic idea being that if you think that the world is uncontrollable, then of course any computations of your expected reward will give lower results. If you can't control the world, then you cannot expect much reward. The same thing applies to recognizing the uncertainty. If you are not certain about what happens in the future, well, it actually implies uncontrollability as well. And then, well, also your expected reward will go down. So here's one fun quote from Epictetus about a kind of an attitude that you might adopt. So if you are going to bathe, picture to yourself the things which usually happen in the bath. Some people splash the water, some push, some use abusive language, and others steal. So this is clearly a case of decreasing your expectations. So if you go to have a bath in a public Roman bath, with this kind of attitude, then you will expect less enjoyment, less nice things, and then you will have less reward prediction error and less frustration. So that's intervention number one. Intervention number two is to reduce certainty attributed to the perception. Now, as I said earlier, well, the reward might be misestimated because the reward is simply a percept, and perception is a case of probabilistic inference with a lot of uncertainty. For example, you might ask that if you feel the taste of sugar in your mouth, is it a positive reward? Well, it may kind of feel good, but I mean, it's actually bad for you in the long term. So it is rather reasonable to think that an uncertain reward loss should actually lead to a weaker frustration signal. If you are not certain about the reward loss, then you shouldn't make any strong signals. In fact, this idea can be formalized strictly. As a very simple illustration, we can consider the classical problem of estimating the average of many when we have many data points xi. Now, the optimal estimator in the classical mean squared error sense is that you should give less weight to those data points with more noise. So assuming you have some idea of the noise level in each of the data points, which I denote here by sigma I. So then it turns out that the optimal estimator for the average or the mean parameter is a weighted average where the weights are basically proportional to the inverse of the noise level. And this thing in the numerator is just a normalizing term. And in fact, this thinking, well, this is just intuitive, but actually it can be made completely rigorous in the framework of reinforcement learning that has been done by May and others in ICLEA, ICLEA a couple of years ago. Okay, and then there are many interventions. Yes, a third intervention, actually more like a very broad kind of intervention with many different aspects, which is meditation. So this is really a central method in Buddhist training. What I said earlier is perhaps more equally applicable to Buddhist philosophy, Buddhist training and Stoic training, but well, the kind of in some sense almost a unique contribution of Buddhist philosophy is the idea of meditation. So, well, the basic method of Buddhist meditation could be characterized as follows. You focus on something, typically your breathing, thus making the mind relatively empty, and then you observe the mental phenomena that appear in your mind. Interestingly, simply doing this simple thing often leads to feelings of joy or even some kind of a bliss. That's what many meditators report. Now we can actually use some of our theories I explained earlier to give one possible reason, which is that actually when you make the relatively empty and focus on the breathing and observation of mental phenomena, you are actually not simulating in the sense of wandering thoughts. You are not simulating the future or the past, not replaying the past. You are kind of meditation is kind of preventing that. And thus you are preventing simulation of frustration as well. This is just like a kind of probably only a small part of the explanation. I think actually the question of why meditation kind of gives you feelings of joy is very deep. And I don't claim this is the final answer at all. But another interesting thing about meditation is that it can actually, I'm kind of assuming that maybe one of the basic, most fundamental effects of meditation is that it speeds up the learning. Because, well, basically we have a learning process in the training that we had earlier. We want to learn that the world is uncontrollable and there's a lot of uncertainty, or what they call impermanence in Buddhism. So now in meditation, you can actually see uncontrollability of your own mind, because the mind usually starts wandering, and you can even see uncertainty and impermanence of your perceptions, which are changing all the time. And now, perhaps a bit paradoxically, the emptiness of mind actually facilitates the observation of these things, partly because then there is not too much content in your mind, and you can focus on some specific things like how the mind starts wandering. And meditation has many different effects. Another extremely important one is that it trains metacognition. And this metacognition may actually enable you to stop processing that leads to desire. So basically you observe kind of what happens in your mind on a metacognitive level. In the book, I have actually a rather detailed description of this kind of a loop that starts from like sensory input from the world. Then there's a lot of information processing, including all these things like desire, planning, and so on, and computation of error like frustration. I will not go into details, that's too much. But okay, here's a very short description of that cycle, which is that there's a stimulus, there's desire, action, and then possible frustration. Now, the point is that if you are able to metacognitively observe this, you may learn to stop this cycle, so that there is no frustration, which is the possible outcome of the whole process. So you can observe desires, for example, and maybe you can just kind of relax the desires, let go of them, or you can let go of planning or so on. And you can basically somehow stop this cycle at some point, so before it gets to anything like frustration. Okay, that was it. Here's a conclusion. So I modeled suffering here primarily as frustration, and I gave two different but closely related computational definitions, which are either it's a failure of a plan or computed as reward prediction error. In fact, failure of plan can be seen as a special case of the reward prediction error. And we saw very clear connections to Buddhist and Stoic philosophies, which also posited that, well, human suffering is mainly a question of frustration. But there was another additional theory, which is that suffering comes from threats, which then led us to the theory of distributional reinforcement learning, which we can formalize the idea, the concept of threats inside that theory. But one of my points was that threat is actually always a threat about frustration, and thus we can in some sense reduce threats to frustration. And then the second part of the talk and the book is about root causes of frustration and suffering, some of them being, well, basically there's insufficient data and insufficient computation, so the system makes errors, our brain makes errors, and in particular this leads to phenomena like uncertainty and uncontrollability. And at the end then we develop various kinds of interventions, where basically on the one hand the agent manipulates its own world model. It basically kind of tries to change the way it sees the world, for example by reducing expectations of reward, or acknowledging things like uncertainty, uncontrollability, and so on. And on the other hand then there is this idea of metacognition that then allows for more control on the processing, so that you can stop this processing when it somehow like is approaching frustration. Okay, that's all. Thank you very much for your attention.
So are you open to questions?
Definitely, yes.
Does anybody have any questions? You should maybe come here. I don't know if you could hear you from back there.
Is there like a significant difference in the efficiency of each intervention, or do they like work very similarly in reducing suffering?
Oh, that's a difficult question. I don't really know. Of course, the interventions that I presented here, they are in some sense like not kind of comparable, because meditation is a very kind of rich, almost like a class of interventions. Or I should perhaps say that if you do any kind of meditation, it will probably work on many different mechanisms. So from that viewpoint, I would expect that meditation may be the most efficient one, simply because it's kind of many interventions packed into one. Yeah, okay, that's actually a very good question. Nobody ever asked me that, so I don't really have a good answer. But I would guess meditation is probably one of the best things. And of course, we see that in the modern world, a lot of people are taking up meditation practice. Not that many people are talking about reducing expectations, which may be a pity, actually. People are kind of forgetting this kind of a slightly more cognitive philosophical interventions. Yeah, okay.
So when you talk about reducing expectations, is there not also a danger or a risk in limiting your expectations so much that you never do anything, therefore limiting your excitement for life, which would then possibly lead to suffering on its own?
Yes, that's in contrast to the previous one. Your question is actually a kind of a very widespread kind of a counter argument to this kind of thinking. Something like that has been kind of people have been criticizing Buddhism and Stoicism and so on, I think, for centuries, based on that idea that, okay, if you reduce the expectations, or like in the case of Buddhism, people often talk about reducing desire, which is another intervention which I discuss in the book, although I didn't talk about it here. Reducing desires is closely related to reducing expectations anyway. So yes, I suppose there are probably some risks. I discuss in the book why they might not be that serious. Well, maybe the one thing is that, well, first of all, I think these interventions are actually rather difficult. So it may not be very likely that anybody would be able to reduce the expectations so much that it would actually go to a pathological level. It's not excluded, especially like maybe if you have maybe your expectations are very low naturally, and then you reduce them even more. Maybe it goes too far. That is a possibility. So maybe actually that kind of ties to the first question, which is that in some sense it might be optimal that you choose the best interventions based on your own, personality, temperament, and so on. So maybe it's quite possible that for some people reducing expectations may not be an incredibly good idea. But another answer to the question is that, well, I talk about in the book about these self needs, which I just mentioned here, but I didn't talk about them, where the idea is that there's another system that's actually evaluating your long-term rewards and kind of punishing you if you don't get any rewards in the long run. So that system kind of counteracts this kind of a completely depressive thinking where you don't do anything, because then the higher system will actually evaluate that now you are performing badly as a whole, as an agent, and then it will basically force you to do something. So yes, but it is definitely true that, well, yes, things are a bit more complicated than especially explained in this book, and yes. Things can go, if you go, I suppose the one thing point is that if you go do anything too far, if you take anything too far, anything good, if you take it too far, it may be actually bad.
Hi, Professor. So I heard a lot of talks about pain and pleasure today, like dopamine and suffering. It seems like a debate here, but I'm getting a little bit tired of it because everybody is talking about it. I'm very interested in models, so I want to know your opinions. Are features explicit or latent? So whether you can put the models or neural network features in this box of pain or pleasures. So what are features? Are they secrets and unmeasurable, or are there some intersection, or are they invariant eigenfunctions? Like, can you give me some metaphors for features in this box of pain and pleasure? Another question is that how possible is that something like nonlinear SA can explain neural network features? If it cannot, and it is not the right tool, then what could be the right tool to explain neural network features?
So about what kind of features we should use to calculate these quantities. Is that basically your question? And whether it might be nonlinear ICA or something completely different?
I think my question is that you talk a lot about pain and pleasure, which should correspond to optimization or cost function rewards, right? And desires, right? So I'm wondering, if I look at a model from the perspective of models, neural network features are never explainable, but you talk about how you train them, right? Like using reward function or cost function. Is there a role of features in these explanations or rhetoric?
Okay, I'm not quite sure I understand your question, but well, maybe one point is that, well, actually this theory is very much about reinforcement learning. So it is not really, it's basically kind of a completely different domain from something like nonlinear ICA, where we talk about unsupervised learning features from your data. In that case, when we talk about that kind of feature learning, it makes no reference to anything like reward, right? So while reinforcement learning then is all about reward. So I'm not quite sure if I understood your question or whether this is relevant, but then I suppose then the question is whether, yeah, we could pose the question of how we best approximate the rewards. I mean, as I said, reward is the results. Reward from the viewpoint of the agent is result. It's a percept. It's a result of an extremely complicated sequence of chain of computations. This is something that is not often taken into account in reinforcement learning. In reinforcement learning theory, as it is usually done in machine learning, the reward is just taken. Somehow it comes without any perceptual effort. It just comes exactly. It's just taken exactly and put into the algorithm. But in the case of a real agent, a biological agent, reward has to be estimated, and reward loss has to be estimated. And then you can ask that what kind of features you should calculate from your perceptual input, such that you can actually compute a good estimate of the reward. And well, then we could use all kinds of methods for feature extraction, perhaps even nonlinear ICA. Yeah, maybe, but then that they would only give perceptual features from which then you would use. I mean, you could take calculate nonlinear features with something like nonlinear ICA, and then use something like, for example, linear reinforcement learning algorithms that then take these features and calculate linearly from them some the quantities related to. Sorry, I'm actually talking about quantities related to value functions, but also maybe the rewards. If we assume those has to be the perception of reward is difficult. Okay, this may not have been actually an answer, just some rambling. Sorry.
I can explain a little bit more, because you
Yeah.
talk about Stoic teaching, right? And
Yes.
Buddhism. It seems like what you take away from those philosophies are just reducing desires or controlling desires, right?
Yes.
Meditation and desires, all of those. If I look at the Stoic teaching, then they might be looking at some contrastivity or comparison of two quantities like hot or cold, or these kind of philosophies. It seems like you throw away all those stuff and just look at reducing desire, which is just a lifestyle issue. So my question is that how do you link this to what they are actually saying? It's like I have two different extremes, like what is hot, what is cold, and what is the metaphysics of the philosophies.
So, sorry, I'm afraid I didn't quite understand your question, but maybe I should just comment that yes, often these philosophies are formulated as reducing desires. Yes, that's kind of yes. I'm here more focusing on probabilistic concepts like expectations and uncertainty, but they are strictly related to reducing desires. That I didn't talk about that in these slides, but in the book I explain how all is actually related to desires, and you could actually formulate everything in terms of talking about desires. But it's just desire is not like a well-known, well-defined computational concept. I give some kind of a definition, but it's not like a well-known thing. So that's why I try to reduce desire in a sense to these well-known computational ideas. But I'm sorry, I don't quite understand your question, so I'm not really able to answer.
Yeah.
So is there a risk under this model where an agent could try to totally control its external environment to minimize its prediction error, and then it becomes a homogeneous world?
You said that the agent might try to completely control its environment.
Yeah.
Yes. Yes, I think that would be a risk. So yes, I suppose we are talking about like an AI agent, not a human being. Yes, an AI agent in a certain kind of a world where it might be able to actually completely control the environment. Yes. In fact, I mean, if you want to reduce frustration, well, one way of doing that would be that you actually somehow gain complete control of the world. And if the world is such that an agent can actually obtain that, then that may happen. And yes, you are right that that is a kind of a risk for something that we should consider if you want to do like safe AI. Yes. It's actually related to one question to which I don't have an answer, which is an open research question, which is that now when we train AI agents, well, they are trained by maximizing future reward in the basic framework. If you actually start training, if you actually program an AI agent so that it will minimize frustration, how does this actually impact its behavior? How does it change its behavior from the case where it's maximizing reward? I think this is a very interesting question and related to what you were saying. So that do you then actually get some really weird kind of phenomena? And is this something that we should somehow take into account in agent design, even maybe be worried about?
Where can we learn more about that? Like this difference.
Sorry, I can't hear you very well.
Yeah.
Where would what are some good resources to look into the differences of observed behavior with these different reinforcement schemes?
I don't know if there is a lot of such literature. It's more like, I mean, what I just mentioned is, I think, a completely open question. I don't think there's probably no published literature yet on that. So all I can say is, well, just read my book, please. And I'm not sure if there's any, if I can recommend any other literature. This is kind of a very new topic, you know. So there's almost nothing published otherwise.
I don't know if I can move through. Sorry, there's one question coming in a second.
Hi, so my background is more in like behavioral analysis and psychology, but do you think like non-parametric models like like the time series models are the better method that could capture like that kind of metal like wandering thoughts, like especially in like playing and stimulation of passive event, because those data, behavioral data can be like highly individualistic, and they may not like follow clear functional form. So do you think like a non-parametric time series model can be like better to capture this kind of wandering thoughts or in behavioral data instead of like like part of the reason?
Sorry, did you say in autistic people?
No, I mean just like behavior data can be like highly individualized, and they may not like follow a clear like functional form. So my main question is that do you think like non-parametric statistic like a time series model is like a better approach to like capturing like the wandering thoughts data?
Are you talking? Okay, so what kind of data are you talking about? Behavioral data? Sorry, not brain imaging. No.
Especially in like replaying the past event, what you mentioned, like so the replaying of past events, like we can kind of just record them, like for example, like where you have like bunch of like survey respondent, then those respond may not always like follows like certain of like this distribution. Oh, I have a distribution. So do you think like non-parametric like statistic is like a better or can you like incorporate like non-parametric statistic in your research?
So you mean we have like psychological data, perhaps behavioral data from like some experience sampling kind of stuff, life surveys, and how we can then analyze wandering thoughts in them. Is that your question, roughly?
I'm just asking if you like non-parametric statistic is like a better way to capture this kind of data. That would be the essence of it. Instead of maybe like
Well, I think it's very difficult for me to say anything about knowing like really about the details of the data. Just like very generally speaking, I would say that, you know, non-linear, non-parametric models are perhaps a bit overrated these days because they are so fashionable that people are using them like on any data. But the fact is that you need a lot of data to make those such models work. So if you have only a moderate amount of data, then should probably think about like linear models or some kind of very, very simple models. This is just that would be my kind of my general comment. Otherwise, it's a bit more difficult to say anything in more detail, I'm afraid.
thank you for
I actually have something of a follow-up question regarding what she was talking about. I work with non-parametric models of entropy right now, but I see wandering models, or sorry, wandering thoughts, you call them, as a way of kind of artificially generating data points, like you were saying. So would it, how do you, or maybe you know more than I do. I'm just kind of rambling right now, but what do you think that it would be suitable for to use this idea of wandering thoughts for non-parametric models? And if so, how would we be able to simulate that? Because I'm guessing that in many cases people use something like noise and just inject that into their wandering thoughts to simulate this, or into their recorded sample and inject noise and try to use that to generalize. But perhaps you have some better insights on that.
Yeah, well, I think, well, of course, in reinforcement learning, we have very clear ideas on how to use the wandering thoughts or something similar to wandering thoughts, and they are being used all the time. So there's experience replay, and there is also the idea of like simulating future things. Like the earliest model was this Dyna by Sutton, and often I think in policy graded methods it's often done implicitly. But okay, that's reinforcement learning. But okay, I think you are talking about like entropy estimation in like without reinforcement, right?
Yeah.
Yes. So that's actually I have been thinking about how to use these ideas. I think they probably can be used. So we have the replay part and the kind of planning part. So I think the replay part would mean something like that. Okay, you think that. Well, okay, one thing about replay is that, well, you don't replay everything that you have seen yesterday. You select some of the data points, some of the episodes, and then you replay them in your brain. So now if you like take this to statistical estimation, what it would mean is that you basically like, you somehow privilege certain data points. And maybe like if you have a stochastic gradient method for learning any machine learning method, well, you could devise some kind of a method for choosing those data points that you want to present at every point, at every time point, every iteration. So you can somehow like rank rank the data points that you have. I actually once played around with some kind of a model that would actually do this, but I didn't get anywhere. But I think this is an idea that must be quite useful. It's a bit related to like the idea of core sets. I don't know if you heard about that, which means that you try to like you have a big data set, you try to represent it by a smaller number of points, which are hopefully representative, and then you can do learning with a smaller number of data points. A bit related, but I don't know. I'm not quite sure. But anyway, I think there's something very interesting. Some very interesting methods could be developed in that sense. And then there is the other thing about planning, which is related, as you said, to the idea of generating new data points. So synthetic data. And I think, okay, I think synthetic data is kind of, people are talking about it so much these days. So it is supposed to, solve many problems. Yes, not only like, well, you can add a little bit, you can add noise to like regularize your stuff. Or then I think people are just like synthesizing completely new data points and then claiming how in various ways they improve the learning of any machine learning algorithm. I don't know the literature, but I think a lot of people are doing exactly that. And it is kind of analog to this idea of planning in wandering thoughts. Yes.
Okay. I still want to know your opinions about the models and neural networks, like because the rewards and the costs are more like this kind of a functions, objective function for AI, right? So I want to know your opinion about the model and neural networks because there are a lot of mysteries around it, right? We cannot explain the features. We cannot explain gradient descent or backpropagation. So what are your thoughts on that?
Yes. Okay. So I suppose, okay, so there's two different cases here. One is reinforcement learning, which of course we can have deep reinforcement learning where we learn a neural network in terms of reinforcement learning. But again, I think what you're talking about is like much more fundamental. Just
I'm very familiar with TD learning and Q learning and all those stuff, and I took a lot of courses on like random processes. Because I know there are two parts, right? The objective and also the model. But I want to know your opinions on the model and neural networks.
Model, with model, do you mean like the architecture?
Yes. You can think of model as humans, right? And humans all have objective, but you talk a lot about the goals and objectives. So I also want to know your aspect on the model itself.
Okay, I'm not quite sure how to understand your concept of a model. Okay, so the way I see it, okay, so if we go back to like basic reinforcement, basic deep learning theory, so then we will have the objective that is being maximized, which is maybe prediction error or classification error, and then we have the architecture of the model. Which is like, whether it's a simple multi-layer perceptron or, a CNN or something. But I don't know if you're talking about this distinction at all. Are you?
Honestly, I don't think there are too many mysteries around the reward, right? The reward cost, it can be mean squared error or your reward function or your planning objective function, all of those. But if you think about this in this perspective, right? Because we are talking about a lot of philosophies like pain, pleasure, and all of those. The model is also a very major aspect of it. Because if you don't have a model, you don't have anything to train, right? You don't have anything to perform. And you need this model. But in neural networks, we really don't have any good explanations, like this kind of philosophical explanation for the models, right? If I say my pain and pleasure is to train this model to perform a certain task, then what is the role of this model in this perspective? In this like kind of explanations using pain, pleasure, suffering, dopamine, or anything. So it seems like we greatly ignored the model, but talk a lot about the objective function. It seems to me a little bit reversed, right? Maybe we should talk more about the model and less about the objective function.
Yes. Well, I mean, for me, when we talk about reward, it's always in the case of reinforcement learning. So it's not about general objective functions. If we talk about like supervised learning or unsupervised learning, we have objective functions, but I wouldn't talk about them as reward. So like in my talk, so when I say reward, it is always in the specific case of reinforcement learning. So what you call model is maybe then, I think it may be what I would call an architecture of a neural network. So it is the way that a nonlinear function is being approximated by the system. And then it is this architecture together with an objective function, which may be like least squares or something, that then gives rise to the learning. So now if you say that people ignore the architecture and look at mainly at the objective, yes, many people do that. Actually, I do that most of the time, because one reason being that the architectures are so difficult to understand. So, I mean, nobody really knows why like CNNs work that well or why transformers work well and so on. It's very difficult to say anything about them. But the objective functions, they often have a very clear basis in some mathematical theory. Like least squares is, or logistic regression objective. They are well-known stuff, and now reinforcement learning, we have this total sum of future rewards. It's all mathematically very well defined, and we can understand. There are theories to understand these things, but then choosing between the architectures, it has always been like mainly just empirical. So you just try out different architectures. Some of them work and others don't. Now, if you could actually theoretically analyze these architectures better, that would be great. And of course, people are trying to do that. But I think it is really difficult.
I want to know your opinions. Is there a philosophical explanation for the architecture instead of the objective?
Not from my viewpoint, at least. So for me, any philosophy that I use here, it's always related really to the reward. So the reward, and not any objective function, not ordinary objective functions as in supervised learning, but always the reward in the sense of reinforcement learning. So this is all about reinforcement learning. The theory in this talk and this book is really almost all about reinforcement learning, and it doesn't necessarily need even neural networks. You could do it in a very, very basic reinforcement learning scenario where the world is really completely discrete and you have what is called tabular learning. That is, you just like store the value of each state. So from that viewpoint, neural networks are something a little bit like something that is not necessary, which is not kind of, you could talk about the theory of this book or this talk, completely ignoring neural networks. Neural networks might just necessarily appear in the case of perception, and they probably explain a lot of stuff, what happens in the brain, because the brain does use neural networks. But most of the theory is really like independent of neural networks.
Well, thank you so much for this, Dr. Hyvärinen. I personally have really enjoyed this, and I'm pretty sure everybody else has too. We have to move on now because we've made Dr. Wagner wait a little bit, but we really appreciate your talk today, and I hope you have a great rest of your day.
Thank you very much. It was really my pleasure.